Hi, Professor.
Hey, Kevin. Hey, D. Yak. Oh,
Hello.
Sebastian, you're also here. Good, welcome. And so this is actually combined. I invited all my lab members to join our FISP presentation. So we are going to have D go first, then Kevin, then myself. Okay.
Sounds good.
All right. So remember, you have 25 minutes and leave 2-3 minutes for some discussion. After that, we switch to another presenter. So 25 minutes max, everyone. Okay.
Okay.
All right. So welcome, everyone. Let me see how many people we have. Let's see. We have 8 people. That's a good number. So please watch your time. I'll give you 5 minutes. When you hit the 20 minutes line, I'm going to give you a signal.
Okay.
Otherwise, you have full control of your time. So
Okay.
now the floor is yours. Okay.
Okay. So let's
ahead.
start. So today I'm going to present a global monotonic tracking control of multivariable system. It's the EECS linear multiple control, the final presentation. This paper is read by the Lerazon and Jane and Augusto. So we have the outline here. I'm gonna introduce background related work on problem formulation, solution to problem, conclusion, and future work. So first thing first, in this paper, I present a method for designing a linear time invariant state feedback controller to monotonically track a constant step reference and any desired rate of convergence for any initial condition. Necessary and sufficient constructive conditions are given to generate a monotonic step reference from all initial conditions. This method is developed for multiple input and multiple output systems, and can be applied to square and non-square systems, strictly proper and non-strictly proper systems. And importantly, also minimum and non-minimum phase systems. The framework proposed here shows that for MIMO LTI systems, the objectives of achieving a short setting time while at the same time avoiding overshoot and undershoot. The problem of improving the shape of the step reference curve for LTI system is as old as the control theory. For example, heating or cooling systems, elevator or satellite positioning. The common element in these problems involves designing a control input for the system to make the output take a certain desired target value and keep it there. A fundamental issue in classical feedback control is the design of control laws that provide good performance, both at steady state and during the transient. The steady state performance is typically assumed to be satisfactory if once the transient is finished, the output of the system is constant and equal to the desired value. When dealing with the transient performance, one is usually concerned with the task of reducing both the overshoot and undershoot, or ideally of achieving the monotonic response that rapidly converges to the steady state value. It is commonly understood that objectives of achieving a short setting time while at the same time avoiding overshoot and undershoot is also the challenge of this paper. Well, this case is easy for CISO system, but the control method the authors developed in and implemented in this paper challenge is how to avoid overshoot and undershoot for the MIMO system. The authors show in particular that in the case of LTI MIMO systems, it is possible to achieve arbitrarily fast setting time and also monotonic step reference in all output components for any initial condition, which implies the avoidance of overshoot and undershoot even in the presence of the non-minimum phase invariant zeros. For the related work, number 25, 13, and 10, these 3 papers are dealing with the general tracking control problems, a so-called model matching problem. So a model matching problem is to design a controller to make a transfer function. It's the same with the closed loop system transfer function. While this method does not, in general, yield a solvability conditions expressed only in terms of the system structure. A recent contribution offering design method for MIMO system, which is in 21. This paper proposed for the design of the state feedback controller to yield a non-overshooting step reference for LTI MAMO systems. Importantly, this design method is applicable to non-minimum phase systems. It doesn't assume that system state is initially at static and can be applied to both continuous time and discrete time systems. Very recently has been shown in 22 with papers is how the method can be adapted to obtain a non-undershooting step reference. The key idea behind the approach in these two papers is to design a feedback matrix that achieves the desired closed loop eigenstructures. That only a small number of the closed loop system modes appear in each component of the tracking arrow, which is defined, this tracking arrow is defined as the difference between the system output and the desired target value. Indeed, if the closed loop eigenstructure can be constrained in such a way that each component of the closed loop of the tracking arrow is driven only by a single real valued closed loop mode, which is exponential in the form e to the power of lambda t in the continuous time. However, a key limitation of the design method given these two papers is a lack of analytic conditions expressed in terms of the system structure that guarantee the existence of the state feedback controller that give the desired transient response. In other words, the method of these two papers does not provide a structure criteria to decide if the problem is solvable in terms of the problem data, and doesn't guarantee feedback matrix a singular one, and also solve in any initial condition. So thus, in this paper, for the first time in the literature, a complete answer to the problem of achieving global monotonic step reference for MAMO LTI system is provided. The authors show that MAMO LTI system, the presence of non-minimum phase invariant zeros, does not prevent the global monotonic step reference to be achievable. Indeed, even in the presence of one or more non-minimum phase invariant zeros, if the feedback throw matrix is allowed to be non-zero, it may still be possible to achieve monotonic step reference from any initial condition for any constant reference signals. So next part is about the problem formulation. Consider a LTI system, sigma. We assume that no less of generality of all columns of BD and also assume that all rows of the CD is a linear independent. So if there exists the tracking arrow epsilon, that when the time goes to infinity, we use the y0t minus yt to let this value equal to 0. Then we call this system is non or zero steady state arrow tracking. In this paper, we are more concerned with the problem of the design of the state feedback control law for this guy, such that all initial conditions, the output y checks a step reference r belongs to y with a zero steady state arrow and is monotonic in all components. And also we have the assumption 1.1 here, so which is a sigma, system sigma is a red invertible and stabilizable and has no invariant zeros at the orange. So first thing is the tracking control problem. Given a step reference R belongs to Y, and choose the feedback gain matrix F, such as A plus BF is asymptotic stable. This is always possible since there's a pair AB is assumed to stabilizable. Let us to choose two vectors, which is XSS and USS, that for given R belongs to Y, satisfy this guy 0 equals to A XS and plus B USS, something like that. And such a pair of vectors, XSS belongs to X and USS belongs to U, exist under this kind of the conditions. First, these conditions red invertibly ensures the system matrix, Rosenbrock matrix, which I'm gonna introduce later, is full row rank, and we already record the values lambda belongs for which this Rosenbrock matrix rank are invariant zeros of sigma. The second thing is in the continuous response, the absence of the invariant zeros as orange guarantees that matrix Rosenbrock is full row rank. So now applying the state feedback control law, And we have the ut equals to fxt minus xss plus uss. And using the change of variable, we call this x equals to x minus xss. Give the closed loop feedback system looks like that. So since a plus bf is symplectic stable, x converges to xs, and this x converges to 0 and y converges to r as t goes to infinity. So we are more concerned with the general problem of finding a gain matrix such that a closed loop system obtained using this function, function 4, that can achieve monotic response and any desired rate of convergence from all initial conditions. We shall describe this property as globally monotonically. We describe the problem as follows in terms of checking error epsilon t, which is equals to yt minus rt. We can get this matrix. So here, I'm gonna propose the problem 1. So let row belongs to real number and the row less than 0, which is row should be the eigenvalue of the matrix in the continuous time. Find a state feedback matrix F such that applying control law with this F to sigma yields and asymptotically stable closed loop system sigma out, for which the checking error term epsilon t converges monotonically to 0 at the rate at least the row in all outputs from all initial conditions. If we are able to obtain a checking error epsilon t that consists of single exponential per component in continuous time, we can choose each lambda k in such a way that lambda k less than row less than 0 in the continuous time. Then we solve problem 1. Indeed, why? Because asymptotically stable exponential of lambda k are monotopical functions. This suggests that a possible way to solving the problem 1 consists of the solution of the following problem, which is problem 2. So for the problem 2, let row less than 0, find f feedback matrix such that applying control law with this f to sigma yields an asymptotic table. Close the loop sigma epsilon out, sigma out for which from all initial conditions. The checking error terms given by, which is also the function 8 for some real coefficients beta k. And this beta k depending upon x0 and for some real values lambda 1, lambda 2 to lambda p, which satisfying in the continuous time less lambda k less than row less than 0. So clearly, solutions to problem 2 also solve problem 1. So here about the solution to problem 2 is for the lemma 1. Problem 1 is equivalent to problem 2. So how to solve it? Prove. Let row less than 0 and let matrix F and lambda 1 to blah blah until the lambda p solve problem 2 with respect to row. Then outputs epsilon kt satisfy the function 8 and 6. Next, assuming that feedback matrix F solve problem 1 for a certain row belongs to R negative, the checking error is the output of the system sigma out, and its components can be written as epsilon kt equals to c plus df k e to the power of a plus bf t small x 0, where c plus df denotes the kth row of the c plus df, and let us write the pair of the c plus df and a plus bf in a standard observability form, in which the observable part is in turn expressed in the observability canonic form. Accordingly, so it looks like this, and accordingly, the small x0 we can write in the new way is written in the closed look like this way, and also we apply the Laplace transform function to the epsilon kt. We got this one, and which is we show this numerarity of this one and it's polynomial, and the denominator is also a polynomial of the observer part of the c plus df and the a plus bf. By suitable choosing the initial condition, which is small x0, and the degree D and of the numerator can be selected arbitrarily in the range of from 0 to L minus 1, and beta k. And this beta k is the coefficient of the numerator. Thus, epsilon kt is a linear combination of the modes of the observable subsystem with arbitrary coefficients, and can be written as this guy, where the lambda 1 to lambda p is a real eigenvalue of the observable subsystem, and with the associated algebra multiplies m1 to mv, and where the mu1, mu2c, and mu1 bar to mu2c are the complex eigenvalues of the observable subsystem, and associated with the mu1. So where I'd like to talk more about these functions, and also for the beta k, also for the sigma. For sigma I is about the real part of the ui, and also the omega I is the imaginary of the ui. Finally, the real coefficients, which is the beta k, beta k hat, and this beta k hat double prime can be made by choosing suitable initial conditions. In particularly, we can pick one of the L modes appearing in this function and select the initial conditions in such a way that epsilon kt in that model. Since by assumption the response is mononomial from any initial condition, only components of the form exponential lambda it for real lambda I can appear in each epsilon k, because for any real lambda k less than 0, the function t to the power of g minus 1 exponential e to the power lambda t is mononomial only if g equals to 1. Well, the function is the function t is to the power of the g minus 1 exponential sigma t sigma I t cosine omega t, and about this guy. In other words, the polynomial denominator can only have real simple negative roots. So thus, for each component epsilon kt, we have the epsilon kt looks like this one, and then crowding to lemma 8.1. So this, if the epsilon kt is a linear combination of 2 or more negative real exponential functions, it will change sign, and hence not be mononomial for real values of the coefficients beta kt. Thus, for each k belongs to 1 to p, we must have epsilon kt, which is equals to beta ki tilde times e to the power of lambda it for some eigenvalue lambda I and some real coefficients beta k. So thus, problem 2 is solved. So next part is about global mononomial setting. In the previous section, we observed that in order for the problem of global mononomial checking to be solvable, we need to describe at most p modes evenly into the checking arrow with 1 mode per arrow component. To achieve this goal, all the remaining closed loop modes have to be made invisible from the checking arrow. If it is possible, then step reference guaranteed to be mononomial for any initial condition, and therefore also non-overshooting and non-undershooting. Our aim is to find the conditions under which the gain matrix F can be obtained to give the single mode structure, which is that structure is given function 8 for any initial condition. Consider we have the sigma out here, and which can be written as this guy, where the omega t equals to f times small xt. Clearly, sigma out can be identified with the ABCD. The task is to now find the feedback matrix that new control omega t equals to f small xt that guarantees for every initial condition x0 belongs to x, the checking arrow epsilon t is characterized by a single stable real mode per component. Well, let j belongs to 1 until to the blah blah until to the p, and let lambda j belongs to eigenvalue matrix. Consider a solution Vg and Wj of the linear equation of this guy. where beta j is not equal to 0 and ej is the jth vector of the canonical basis of y. Notice that this equation always has a solution in view of the red invertible of the sigma. By choosing f, such as f times Vj equals to Wj, we can find a plus bf Vj equals to lambda j times Vj, and also this one. So hence, from the epsilon kt function, we know that for in any initial error state small xt belongs to span Vj, the response associated with the control wt omega t equals to f small xt looks like this guy. And where the gamma j depends on the particular initial state x small x0. So considering lambda 1 until the lambda p and the lambda belongs to eigenvalue matrix, by applying this argument for all components of checking error, we obtain a set of the solutions. We have the vi vj vi w v1 w1 until the vp wp. If the v1 until the vp are linear independent, we can choose f to be such f vi equals to wi. Then for every small x0 belongs to span vi until vp, we can find this equation. However, this result can only hold when the small x0 belongs to satisfy these conditions. In order for this response to be available from any initial condition, we also need to render the remaining n minus p closed loop modes invisible at epsilon t. So this task can be accomplished by exploiting the stabilizable output nulling subspace Vj. Vj star can always, which is defined as the largest subspace of the X. The corresponding state feedback generates the state trajectory that asymptotically converges to 0, while the corresponding output remains at 0. We shall see a basis for Vj asterisk can always be obtained as the image of matrix which is V1 from the Vb that satisfies this guy. For some other matrix, W1, W2, and until Wd, where the mu1 and mu-t are the distinct minimum phase invariant zeros of sigma. So the complex, so the mu-t1, so the mu-t1 is arbitrarily stable, and we have the dimensional Vg plus a span V plus until V plus or equals to 1. And then we get some to, when we get to some of the small x 0 can be decomposed as some small v and small r, which is small xv belongs to Vg and xr belongs to this one. So if the dimensional Vj equals to n minus p, we can find the Vp plus 1 until the Vn from the columns of V1 from the Vd from Vi and p. So Wp plus 1 Wn to be columns of the Wj, which is belongs to Vp plus 1 and Vn. So then we can get the F matrix in here. So next part, I'm going to give the solution. Give the not like the solution. It is the example, which is given a non-strictly purport continuous time LTI system, which is we given looks like that. And we have assigned eigenvalues lambda 1, lambda 2, lambda 3, which is equals to -1. Since only controllable eigenvalue is -6. And for the minimum phase invariant zeros, Z1 is -6, and non-minimum phase Z2, Z3, Z4 is 2, 3, 5. So thus we can get the feedback matrix looks like that. So if we have the closed loop eigenvalues are the sigma a plus bf equals to -1, -6. If the reference is R equals to R222. We remember we introduced this XSS and USS at the beginning. We can get the result from here. Also, by applying control law, UP equals to FXT minus XS plus USS, we can get our epsilon t. Epsilon t equals to gamma 1 e to the power limited t and this matrix. So which have the simple mode from the formulation 13. Thus, this system exhibits the globally monotonic step reference. So before I'm going to give the solution to the problem 1, there's the mathematical background. So what's the VG? V star G is sum of the two parts. The first one is subspace the R A star, and the second part is the subspace then the minimum phase invariant zeros of the sigma. And for the R A star, we give the formulation and how to calculate it, and recall the Rosenbrock matrix. Rosenbrock matrix looks like this one, and it helps to transfer from the state space for the transfer functions. And also we get the assumption 1.2, which is system S has no coincident minimum phase invariant zeros. So let assumption 1.1 and 1.2 hold, and let dimensional VG equals to n minus p. So problem 1 is solvable if and only if satisfies this one dimensional VG A star plus sigma to RG, which is greater than n minus p plus curve S. So how to prove it? Suppose this function is not satisfied, which means there exists S belongs to R to the power of 1 until the p.
You got
so
next 5 minutes.
Okay. Which is there exists this one this total dimension. Sorry, there is a total dimension less than n minus p the car plus, which we consider this we plus the lambda j in here, and since the rj belongs to rj lambda j belongs to rj star for all j, and we can write it explicitly, and so we can observe here. So if we add one single rj in here, and we equals to n minus p plus 1, if we write two parts, which is ri plus rj, we can equals to n minus p plus r. If we add all of them, which is expand of the sigma, all sum of this rj from 1 to p with equals to n, which means even if in the single item, the most minimum dimensional is greater than n minus p plus 1. And so which means this one, the smallest value is greater than the largest value. Hence, this function is always greater than the n minus p plus curve S. So proved. And also the paper also gave the computation of the feedback matrix, which is how to calculate the F in here. So conclusion. So this paper is achieving a monotonic step reference from any initial condition in LTI memo systems. And the second thing is important to find the structure conditions ensuring that every component of the tracking arrow consists of the sum of at least two, at most 2, 3, or more modes. For the future work, I may consider to let UAV tracking target and let the UAV fly to the target fast but very stable and do not overshoot. And we can also apply this controller to any dangerous task, which is let our UAV flies more safely. I think that's all for today. Any questions?